Good day, grade 12 learners. Welcome to today's subject lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center and is broadcast by Pagama Research and Development. We have a WhatsApp interactive number. It's 064-748-8913. You'll use that number to interact with us. Right, today's lesson is a continuation of last week's lesson on Euclidean geometry, but today we are going to specifically focus on similarity, since last week you did proportionality. Right. Now we have our lesson objectives. By the end of this lesson, you should be able to prove that equiangular triangles are similar. You should be able to apply Converse theorem that says triangles with sides in proportion are similar, and you should be able to solve Euclidean geometry problems using the similarity theorem. You can refer to CAP's document on page 48. The examinable theorem on proportionality or on similarity. Our examinable theorem is the one that states that equiangular triangles are similar. You can refer to the exam guideline for all the examinable theorems in grade 12. Right, you need this prior knowledge from grade 9 and grade 10, similar polygons, for you to be able to cope with this chapter. Right, proportionality and similarity reasons. We have the following reasons that are extracted from the exam guideline that would be useful for similarity and proportion. Now, with today's lesson, we'll be focusing mainly on the last three, which talks to equiangular triangles or similar triangles, and as well as the converse of that particular theorem. Right, similarity. We're going to start with similar polygons. A polygon is a closed straight-sided diagram with three or more sides. In a polygon, there is many vertices as there are sides. Triangles and quads are 3- and 4-sided polygons respectively. Now, definition. We say two polygons having the same number of sides are similar if they meet both conditions. It should be both conditions. Number one, it should be all pairs of corresponding angles should be equal. Number two, all pairs of corresponding sides should be in the same proportion. Now, this implies that given condition 1 and 2, we can conclude that polygons are similar, or given that two polygons are similar, then 1 and 2 are both true. We have an example, similar polygon example. This is to just test our pre-knowledge. Consider the following rectangles. Check whether they are similar or not. Remember, we said they should meet both conditions. Now, we should test these polygons for both conditions. If both conditions are met, then we're going to say the polygons are similar. But if one of the conditions is not met, then we will conclude that the polygons cannot be similar. Now, let us test condition 1. If you look at condition 1, we have to check angles. If you check angle A, it's exactly equals to angle P, and angle B is equals to angle Q. Angle D is equals to angle S, and angle C is equals to angle R. Now, these angles are equal. Pairs of angles are equal. Now, in similarity, it's also important to look at the order. If you are to check on my left-hand side, I have the left-hand polygon. And on my right-hand side, I have the right-hand polygon. This is the polygon on the left, the one in green, and this is the polygon on the right, the one in red. Now, if we look at condition 1, we see that all pairs of angles are equal. Then we can conclude that condition 1 is met. Condition 1 is met. Then we need to test the second condition. In order for us to test the second condition, we need to look at the sides. Now we're going to start with the side from our bigger rectangle AB. We divide that with PQ to test the ratio of those sides. We get that this is 20 millimeters divided by 10 millimeters. When you divide 20 by 10, we get 2. We move on to side BC. We take the ratio of BC divided by the ratio of QR. We get that this would be 10 divided by 5, which also gives us 2. Now, continuing with this, we need to look at side AD and side CD from the bigger rectangle, as well as side SR and side PS from the smaller rectangle. Now, if we check that these two are rectangles, then we know that pairs of opposite sides are equal in length, which means that DC is also equals to 20 millimeters and AD is also equals to 10 millimeters. Similarly, from the smaller rectangle, we can conclude that SR is given by 10 millimeters, as well as PS is given by 5 millimeters. With that information in hand, we can continue with our pairs of sides. We go now for side CD divided by side RS from a smaller rectangle. We get that this would be 20 divided by 10, which gives us 2. Lastly, we will focus on side AD from the bigger rectangle, as well as side PS from a smaller rectangle. We get that this is 10 divided by 5, which also simplifies to 2. Now you can see that all the pairs of corresponding sides are in the same proportion. Therefore, we can conclude that the two polygons are similar, or rather, condition 2 is also met. Now, if both conditions are met, then we can conclude that polygons, or these rectangles, are similar. These polygons are similar. This is prior knowledge. Let's move on. Right, when you look at the next slide, you can see that I've presented also two rectangles, a smaller rectangle and a bigger rectangle. The instruction is consider each sketch below and state whether the polygons are similar or not. Justify your answers with suitable reasons. Now, we need to test this for two conditions. Condition 1, we check the angles. Now, if you look at the angles, you can see that angle A is the same as angle E, which is 90 degrees. Angle D is the same as angle H, which is also 90. Angle B is the same as angle F, which is also 90 degrees. Lastly, angle C, is exactly the same as angle G. So we can conclude that condition 1 is met because all pairs of corresponding angles are equal. Now we need to check whether the second condition would be met. The second condition deals with the sides. We need to check whether the corresponding sides are in the same proportion. We start with AD from a smaller rectangle, divide by EH from a bigger rectangle. You can see that this simplifies to 3/4. We move on. Side DC of a smaller rectangle, divide by side HG of a bigger rectangle. You can see that this now simplifies to 2/3. Now, if you check 3/4 and 2/3, these two values or these two fractions are not equal. Because of that, we do not go on. We'll just say that the corresponding sides are not in the same proportion. Therefore, condition 2 is not met, or condition 2 does not hold. Why doesn't it hold? It is because corresponding sides are not in the same proportion, or corresponding sides are not proportional. Therefore, the two polygons are not similar. These two polygons are not similar because they meet condition 1, but condition 2 is not met, or condition 1 holds, but condition 2 does not hold because the pairs of corresponding sides are not in the same proportion. Right, moving on. We have another sketch here which represents two parallelograms. We want to check whether these two parallelograms are similar. Remember, to test whether polygons are similar, we need to test both conditions, and they should both hold. Now, if we look at condition 1, for these parallelograms, we see that angle Y, or rather angle A, is the same as angle E, which is equals to Y. So the first pair of corresponding angles are equal. If we look at angle D, it's the same as angle H, which is equals to X. Angle B is the same as angle F, which is equals to X as well. Angle C is the same as angle G, which is equals to Y. Because all pairs of corresponding angles are equal, we would say that condition 1 holds, or we can say that condition 1 is met. Now we need to test the second condition. Remember, with the second condition, we're going to check the pairs of corresponding sides. However, it is important that we test or check them in order. We start with the smaller parallelogram, and then we go to the larger parallelogram. If I test condition 2, if I check the smaller parallelogram, I have side AB, I test it with side EF, AB over EF, I get that this is 5 divided by 10. That's 5 divided by 10. If we simplify that, we're going to get 1 over 2. We move on. We go for side EH, or rather AD from a smaller rectangle, over EH from the larger parallelogram, not a rectangle. Now AD, that's 4 over EH, that's 8. That simplifies to 1 over 2. Right, moving on, we look at side DC from a smaller parallelogram. We divide that with side HG from a larger parallelogram. We get that that's 5 divided by 10, which simplifies to 1 over 2. Lastly, we look at side BC from a smaller parallelogram over side FG from the larger parallelogram. We get that that's 4 over 8, which simplifies to 1 over 2. Therefore, we can conclude that AB over EF is the same as AD over EH, which is the same as DC over HG, as well as BC over FG. Because of that, because we have all pairs of corresponding sides in proportion, condition 2 holds as well. Now, since both the conditions hold, we can therefore conclude that the two polygons are similar. We can therefore conclude that the two polygons are similar. Right, moving on. Now we focus on similar triangles. Remember, triangles are also forms of polygons. For triangles, however, any one of the conditions, any one of the two conditions, equal angles or proportional sides, is sufficient to guarantee similarity. There are two theorems, or rather there are theorems which state that any one of the conditions apply, then one condition will automatically apply as well. This is only true for triangles. Right. Now we can see that with respect to triangles, we only need to check one condition. If one condition holds, then we will automatically say the other condition will hold as well. Right, let's go to the notation. We write triangle ABC, and then we have those 3 vertical lines. Then we have triangle DEF. The 3 vertical lines mean similar to. They mean similar to. So that is the symbol that we use to denote similarity. As you know that in mathematics, we use symbols to communicate. Now, this means that the two triangles are similar. In this notation, the order in which the letters are written indicates the order in which angles are equal. Now, grade 12 learners, when it comes to similarity, order is very, very important. Order is very, very important. We give first priority to order. Your ability to work with these triangles in the order in which you have to work with them will determine your success in similarity. Right. When similar triangles are labeled in this ordered way, it is easy to write down the pairs of corresponding sides. Right. Let me rewrite the similarity statement. Triangle ABC is similar to triangle DEF. Now, if you have this similarity statement, if I can redraw the two triangles, it would mean that angle A from triangle ABC should be the same as angle D from triangle DEF. Angle B from triangle ABC should be the same as angle E from triangle DEF. Angle C from triangle ABC should be the same as angle F from triangle DEF. Now, if you check on my left-hand side, I have the left-hand triangle ABC. And on my right-hand side of the equal sign, I have my right-hand triangle DEF. That order is very, very important. Now, this order in which they wrote this similarity statement does not only give you the order of equal angles, it also allows you to write down in order the pairs of corresponding sides. Now, we normally use what I call the smiling face approach. Now, with the smiling face approach, what we do is we look at the left-hand triangle, AB. I go for AB on my left-hand triangle. Same way as I went for AB on my left-hand triangle, I'll go for DE on my right-hand triangle. That gives me the proportional sides. AB over DE. I can write them in proportion. AB over DE. Now, I can move on to BC. Do the same on the triangle on the right. That would be over EF. Lastly, I'll go for AC. Similarly here, I'll have DF. Now, that is why I call this the smiling face approach, because if you can complete the eyes here, this being the mouth, the eyes here, this being the mouth, then you can see that it's a smiling face. So the smiling face approach in this case gives us the proportional sides in the correct order. Now, moving on. Similarity theorem. Now, this is an examinable theorem. You need to know how to prove it for exam purposes. But for the purpose of this lesson, we will not prove it, we will only apply the theorem. It states that if two triangles are equiangular, so you are given that the triangles are equiangular, then their corresponding sides are in the same proportion, and hence the triangles are similar. Right, there's a shorthand of writing this. When we use it in problem solving, we're going to say that this is equiangular. As a reason, we'll use equiangular triangles, or we'll just use similar triangles. That is when you use this theorem for the purpose of problem solving. Now, if you look at the theorem, we have two triangles, one big, one small. Now, what we notice is that the corresponding angles are equal. Angle A is equals to D, angle B is equals to E, and angle C is equals to F. Now, since these angles are equal, then we can conclude that the corresponding sides are in the same proportion, and hence these two triangles are similar because we used equal, or rather we equated the angles, or we proved that the angles are equal. Right. Moving on. Using angles to prove that triangles are similar. Using angles to prove that triangles are similar. Remember, we have two conditions. We said for triangles, if one of the condition holds, then we can conclude that the other one would hold as well, and hence the triangles are similar. Now, we are going to be testing the first condition in the problems that I'll be having right with you now. Now, when we use angles to prove that triangles are similar, we can prove that two triangles are similar by showing all pairs of corresponding angles are equal. If we can show that any two pairs, very, very important, if we can show that any two pairs of corresponding angles are equal, then the third pair will be equal as well by implication, since we know that three angles of both triangles must add up to 180 degrees. Right. Let me just use a sketch to explain that. Let me use a sketch to explain that. Now, if you have triangle ABC, and we are given that this angle here is, say, 60 degrees, and this angle here is 80 degrees, and we are given a smaller triangle DEF, we are given that angle A is D, which is 60 degrees, angle B is E, which is 80 degrees. Now, we can calculate angle C using the sum of angles in a triangle, or the interior angles of a triangle. If we are to add all three angles, we should get 180 degrees. Now, this would mean that if we are to calculate C, we will get 180 subtract 80 subtract 60, which will give us 40 degrees. We used the sum of angles in a triangle. We can do the same here. We can calculate angle F, we'll also get that, that's 40 degrees. That is why here the last statement says, if we can show any two pairs of corresponding angles being equal, if we can only show two pairs, then we can conclude the third one using the sum of angles in a triangle. Right, moving on. Now we have our first example, using angles to prove that triangles are similar. Right, in this example, you are given a diagram AB, or in the diagram, AB is parallel to CD, AB is 4 centimeters, AE is 2 centimeters, and DE is 3 centimeters. The first question asks of us to prove that triangle ABE is similar to triangle DCE in that order. Now, first things first, we're going to check the given information. In the given information, we are given that there are two parallel lines. Obviously, if we have parallel lines from grade 8 and 9, we know that we should check for corresponding angles being equal, co-interior angles being supplementary, and alternating angles being equal. Right, in this sketch, you can see that only the alternate angles would be applicable. Now, we want to prove that triangle ABC or ABE is similar to triangle DCE. First thing that I'm going to do is I'm going to draw a diagram for triangle, or rather I'm going to redraw or isolate triangle ABE. I'll isolate triangle ABE, and then in triangle ABE, I can see that I'm interested in E1. This is my triangle ABE. This is the one on the left hand side of the similarity sign. And then on the right hand side of the similarity sign, I have triangle DCE. I redraw triangle DCE. I can see that in triangle DCE, I have that the angle E is E2. This is triangle DCE. Now, looking at this, remember, we spoke about the order. The order in which this is written is very, very important. Now, from the statement itself, we can conclude that we should be having angle A being equals to angle D. The first angle from the first triangle on the left is equals to the first angle from the second triangle on the right. And then we can also conclude that angle B is equals to angle C. Also, angle E, in this case it's E1, should be equals to angle E2. That is through implication. However, we need to prove it in order for it to hold for Euclidean geometry. We need to prove that those angles are equal using correct geometry methods. Now, if we check angle A and angle D, we can see that these angles are alternating since we have the two parallel lines. So first things first, to prove similarity, we'll write in triangle ABE and triangle DCE. Angle A is equals to angle D. These two angles are equal because they are alternating, alt angles. They alternate because we have parallel lines. AB is parallel to CD. That is the first one. The second one, if you look at angle B, it's exactly the same as angle C if we use alternating angles because these lines are parallel. So angle B is the same as angle C. We have alt angles because AB is parallel to CD. Lastly, angle E1 would be equals to E2. This can be through implication, it can be implied, or if you look at it, you can see that these are vertically opposite angles. But through implication, we can say that these are third angles of those respective triangles. Therefore, we can conclude here that triangle ABE is similar to triangle DCE. They are similar because all three pairs of corresponding angles are equal. Now, when you look at this, order is very, very important. If you check here, I have my left hand triangle. This side, I have my right hand triangle. In the order in which I wrote my statement, 1, 2, 3, you can see that ABE on the left hand side comes from the left hand triangle and DCE on the right hand side comes from my right hand triangle. That order is very, very important. Right. Now we move on to the second question. Calculate the length of CD. Calculate the length of CD. Now, in order for us to calculate the length of CD, we will obviously need our corresponding sides. We'll need to use our corresponding sides. Now, how do we then get hold of those corresponding sides? We need to go back to the similarity statement and then use our smiling face approach to get the corresponding sides. From the similarity statement, we see that this is for the second one, B. For the similarity statement, from the similarity statement, we can see that we have triangle ABE being similar to triangle DCE. So that's where we're going to start. Triangle ABE being similar to triangle DCE. In this, we have that AB from the first triangle, should exactly be the same as, rather AB from the first triangle should be divided with DC from the second triangle. And then we go for BE should be divided by CE from the second triangle. Right. From there, we can then be able to calculate the length of CD using the given sides. Right, let's check whether we can have something. I have an activity for you. I'll go back to that problem. I have an activity for you where you can apply whatever that we've learned in solving these questions. Now, I have 3 questions, A, B, and C. You are given that A, B, and C lie on the circle. DBE is a tangent to the circle at B, and we need to prove that triangle EBA is similar to triangle ECB, and then we need to prove that BE squared is equals to AE times CE, and we also need to prove that to determine CE if B is 12 and AE is 18 units. Now I'm going to give you 5 minutes for A. Start now with A.
Move the camera. I think that
Step, but it's not writing. No, it's okay. I won't use the eraser again.
yeah, it's better if maybe you erase all.
Oh,
Yeah, erase all.
then everything goes.
Everything clears.
Okay. I'll go back to that problem.
It's fine. I don't know.
Okay. Right, welcome back. Your time is up. Firstly, before we work with A, because I want us to do A together, then I'll give you 5 more minutes to do B and C. But I want us to go back to the problem that we were busy solving and I could not complete. Now, we proved that the two triangles are similar, triangle ABE and triangle DCE, and then we were required to calculate the length of CD. Now, to do that, I said we are going to use our smiling face approach. So we rewrite that triangle ABE is similar to triangle DCE. So to solve this, we go for AB, we divide that with DC, then we go for BE, we divide that with CE from the second triangle. Lastly, we go for the mouth, AE, we divide that with DE. Our smiling face is now complete. Because we used similar triangles to show that sides are proportional, then we're going to indicate that we are using similar triangles to draw the conclusion that we've just drawn. Now from here, we can then look at all the given sides as well as the unknown side. And then I will mark that off from the diagram. AB was given as 4. So I tick that. AB is given. AE was given as 2. I tick AE is 2. DE was given as 3. I tick that DE is 3. Now, if you check from this proportionality statement, inside BE and CE, there is no tick. Because of that, I'll be discarding BE over CE. Then I'll be using the remaining sides. AB was given as 4, divided by DC, which is the unknown, is equals to AE was given as 2, divided by DE, which is given as 3. Now, to solve this, we're going to multiply 4 by 3 and multiply CD by 2. We are cross multiplying. Hence, then, to get CD, we need to divide uniformly throughout by 2. Therefore, we get that CD is given by 6 centimeters. That's how we calculate the length of CD. Right, moving on. This was the problem that I gave you. I said you need to prove that triangle EBA is similar to triangle EBC. Now, first things first, I isolate the two triangles. Triangle EBA, obviously you can also use your highlighters here to just highlight the triangles of interest. To make things easy, I'm just going to isolate triangle EBA. Triangle EBA, I take triangle EBA. This is E, this is A, and that's B. From the diagram, I can see that angle B includes both B2 and B3. And then that's triangle EBA. And then I'll also isolate triangle ECB. Triangle ECB. That's my triangle ECB. I have angle E, I have C, but in the diagram you can see that it's only taking C2, a part of C, and with B, it's only taking B3. Now that I've isolated my triangles, I can go back to the statement. From the statement itself, I know that angle E from the first triangle should be the same as angle E from the other triangle. Angle B from the left-hand triangle. If you check angle B from the left-hand triangle, it's B2 and B3. Should be the same as angle C from the right-hand triangle, that is C2. Lastly, angle A from the left-hand triangle should be the same as angle A from the right-hand triangle. The left-hand triangle should be the same as angle B from the right-hand triangle, and in this case, it's B3. Now that I've isolated, I can then prove my similarity. In triangle EBA and triangle ECB, I can now start. If you look at angle E is common to both triangles. So I would indicate that angle E is the same as angle E, and this is a common angle. This is a common angle. Now, moving on. Checking the second angle in this case, if you look at your diagram, you were given a tangent. And we know our tangent theorems. There are 3. Tangent should be perpendicular to the radius or the diameter. Tangent from the same points are equal in length, and the tan chord theorem. In this case, we have one tangent. So tangents from the same points would not be applicable here. Tangent perpendicular to radius or diameter would not be applicable here as well, because we don't have a radius, we don't have a diameter. Now, if you look at your tangent DBE and you look at the angle between the tangent and the chord B3, it should be equal to the angle in the alternate segment, or the angle subtended in the alternate segment by that particular chord. So B3 is equals to A. So we see that B3 is equals to A. That is our tan chord theorem. Now we go back here in our statement. We want to write that one. B3 is equals to A. But now if you check the left-hand triangle, in the left-hand triangle, I have A. So I'm going to write it as A is equals to B3, following the order of those triangles. This should be tan chord theorem. This is my tan chord theorem. That's the second one. So we proved the first statement, proved the second one. We need to go for the last one, the implied one. We're going to look at the angles that are remaining. Obviously, we proved that E is the same as E. A is the same as B3. We are left with now B2 and B3 should be the same as C2. B2 plus B3 should be the same as angle C2. Should be the same as angle C2. This is our third angles of the triangle. Therefore, we can conclude that triangle EBA is similar to triangle ECB. They are similar because the pairs of corresponding angles are equal. Right, that is the solution for the first problem A. Now for B and C, I'm going to give you a further 5 minutes to do both of them. and then we'll come back and do solutions for both those problems. Your 5 minutes begins now. Welcome back, grade 12s. Now it's time for us to do B and C. Obviously, B and C would need us to use the information from A. Now, we've already proved that the two triangles are similar. So we now want to work with the pairs of corresponding sides. Now we go back for us to work with B. We go back to the similarity statement. Triangle EBA is similar to triangle ECB. Then we apply our smiling face method. Now we go for the left hand eye, EB, right hand eye, EC. This is equals to BA divided by CB, which should be equals to, we now go for the mouth, EA over EB. Now our smiling face is complete. And we say that these pairs of corresponding sides are in the same proportion because these triangles are similar triangles. Now from here, we're going to check, very important, grade 12s. You go to what they want you to prove. You're going to check the sides against the sides that you've written in proportion, and then you're going to tick them one by one. If you check, I have BE squared. So I'm going to look for BE in my pairs of corresponding sides. I'm going to tick that off. So I have EB and EB, and then I need AE and CE. I need AE as well as CE. So I'll go for CE. I've ticked that off. And then I need also AE. I'll tick that off. Now, you see that in one of my sides, there is no tick. So I'm going to discard that side. Now, from here, if I write this alphabetically, I can see that if I multiply this side or I cross multiply the two sides, I'll get that this is BE squared. Remember, B comes before E in the letters of the alphabet. Now, I can now cross multiply this one. I would have AE multiplied by CE. Now I've successfully proved what they wanted me to prove. Done with B, then we move on to C. With C, we are given BE is 12 and AE is 18. They want BE or they want CE. So this is just a substitution problem because BE is 12. Where we see BE in our solution for B, we're going to put 12. So that would be 12 squared is equals to, where we see AE, we put 18, as well as our unknown CE. Obviously, to get CE, we divide uniformly throughout by 18. If you put that in your calculator, it will be 144 over 18, which gives you 8 units. Right. That would be all for activity 1. Moving on. Now we need to use, remember we said there are two conditions. Condition 1, we use angles and we conclude that the sides are in proportion and hence the triangles are similar. Condition 2, we need to work with the corresponding sides. So we can also use corresponding sides to prove that triangles are similar. This would be the converse to the similarity theorem. If the corresponding sides of two triangles are in the same proportion, then the triangles are equiangular and hence are similar. Very, very important, grade 12s. In the first set of problems, we proved that angles are equal and we concluded that sides are in proportion. Now, in the converse theorem, we will prove that the sides are in proportion and then conclude that the angles are equal. Now, looking at this, you see that given triangle ABC and DEF, with, if you are to check the ratio AB over DE, you'd get that this is C over CK, which gives you 1 over K. Similarly, if you work with B over BK, you'd get 1 over K. Similarly, when you work with A over AK, you'd get also 1 over K. So the pairs of corresponding sides are given to be in proportion. The conclusion thereof is that the 3 corresponding angles are equal and hence the triangles are similar. And if we use this converse for problem solving, the reason that we're going to use is sides of triangles are in proportion. Sides of triangles are in proportion. Right. Moving on, you can see that we have an example where we use sides to prove that triangles are similar. We'll move very quickly through this. We have that we need to prove that triangle SPR is similar to triangle SPQ. So what we're going to do here, because we are using sides, we're going to use the order in which the triangles are similar to write down the order of the corresponding sides. And then we check each corresponding side against the other, and if they are equal, then we conclude that the triangles are similar. Now, looking at this, to start off, we are given that triangle SPR is similar to triangle SQP. To start off, we go for SP over SQ. SP over SQ. Remember, grade 12 learners, we are no longer using angles in this problem. We are using sides to prove that the triangles are similar. So we need each pair, we calculate it, we move to the second pair, and then we move to the third one. So SP over SQ. In the diagram, you can see that SP is given by 12. So this would be 12 over SQ. SQ is given by 8 plus 10. That is 18. If you simplify that one, using your calculator, you get that it's 2/3. Now, that is the first one. You move on to the second one. PR as well as QP. PR over QP. Go to the diagram. QR, that's 10 over QP. PR, no, I made a mistake. PR is 6. PR is 6 over QP. QP is 9. That also simplifies to 2/3. Lastly, we go for the mouth. SR over SP. SR is given by, from the diagram, 8 over SP, which is 12. This also simplifies to 2/3. Now you can see that all the pairs of corresponding sides are equal or in the same proportion. Therefore, we can conclude that SP over SQ is equals to PR over QP, which is equals to SR over SP. Therefore, triangle SPR is similar to triangle SQP because sides of triangles are in proportion. Sides are in proportion. All of them are the same or equals to 2/3. Now, what is important here, grade 12s, is that when you prove using sides, you're going to isolate and work with each side. You should not, from the onset, write SP over SQ is equals to PR over QP, which is SR over S. That would be implication when you are given that they are similar. Now you are working backwards. You are using corresponding sides to show that triangles are similar, which means that you have to work with SP over SQ alone, work with PR over QP alone, work with SR over SP alone. And then from there, check those respective answers. If they are the same, then we can conclude, we can write this concluding statement that they are equal, or the equality will hold in this case. And hence, we conclude that they are similar. Right, moving on. Right, because of time, we'll skip this exercise for now and check activity 3. I'm going to lead you through activity 3 in the interest of time, because there's something else that I would like to show you before the end of this lesson. There is the last part, which is very, very important, which you need to know. But now, if you listened to what I said before when I started with this theorem, I said from the theorem, we can conclude that the angles are equal. We haven't done that as of yet. That is tested in this activity. So I'm going to take you through the activity quickly so that we can also be able to answer this question. Prove that PBCQ is concyclic. Now, in order to do that, we need to start with APQ and ACB. We want to prove that they are similar. But if you check here, we are not using angles, grade 12s. We are using sides. It's very important. Now, we will start by writing the similarity statement. Interested in that statement, triangle APQ as well as triangle ACB. I want to prove that they are similar. Now, I will check the ratio AP over AC. If I check AP over AC, I get that this is given by AP, which is 16, over AP or AC, which is 24. This simplifies to, if you use your calculator, you'd get that it simplifies to 2/3. You go for the second one, that would be PQ over CB. PQ over CB. Substituting PQ, PQ from the diagram is 18 divided by CB, which is 27. This also gives us 2/3. Lastly, we would go for the mouth. AQ over AB. AQ is given by 20 over AB, which is given by 30. This is also 2/3. Now, because all these fractions are equal, we can conclude that AP over AC is equals to PQ over CB, which is equals to AQ over AB. They are all equals to 2/3. Therefore, since the corresponding sides are in proportion, then the triangles are similar. Triangle APQ is similar to triangle ACB. Right. Moving on quickly to the second one. Prove that PBCQ is a cyclic quad. Remember, we have 3 cyclic quad theorems. Opposite angles should be supplementary. Exterior angle should be equal to the opposite interior angle. The angle subtended by the same arc or chord on the same side of the circumference should be equal. Now, we want to use the converse of the cyclic quad in order for us to prove this cyclic quad. Now, in order for us to do that, we should use angles. So we go back to our similarity statement and redraw the 2 triangles that were proved similar. It is triangle APQ. I have APQ. It gives me P1 and Q1. I have another triangle ACB. ACB, the bigger triangle ABC. Now, from this similarity statement, I can conclude that angle A from the smaller triangle, angle A should be the same as angle A from that. You can see angle A should be the same as angle A. That is conclusion because the 2 triangles are similar. Now, moving on to the next one, you can see that angle P1, angle P here, it's P1 from APQ, should be the same as angle C. P1 is the same as angle C, as well as angle Q, in this case is Q1, is the same as angle B. This angle here is the same as that angle. Now, if you check that conclusion, you can see that if they want us to prove that this is a cyclic quad, it is evident that the exterior angle of this quad is equal to the opposite interior angle. Because of that, remember here you can use, because of that you can say for the second one B, I will conclude that P1 is the same as angle C. Why do I conclude that P1 is C? Because these triangles are similar triangles. These triangles are similar. Then I can conclude that corresponding sides or corresponding angles are equal. Therefore, I can then say PBCQ is a cyclic quad. I can use any of these 2 reasons. The exterior angle of this quad is equal to the opposite interior angle. Or I can use the fact that this is the converse converse exterior angle of cyclic quad. And that completes the problem. Now, moving on. Very, very important, grade 12s, we need to know how to identify triangles. We are sometimes required to prove equality of ratios and or products without being told which sides to prove similar. In such cases, we have to identify the triangles first. The example in the next slide indicates how this can be done. We are now given ratios and or products, and we are not told which triangles were proved similar. So we need to know how to identify them. There's a method that we can use, and it is indicated in the next example. Now, grade 12s, we are given that PT is a tangent to the circle through T, PAB is a secant with A and B on the circle. Prove that PT squared is PA times PB. Now, when you look at this, unlike the previous problems that we've worked with, where they want us to first prove that triangles are similar, like this one, we first proved that triangles are similar, and then they want us to prove that BE squared is AE times CE. But with this problem, they just go straight to the sides. Prove that PT squared is equals to PA times PB. Now, first things first, we are going to rewrite this product as proportional sides. Then we use that to identify the triangles. Because of time, I won't be able to do these problems step by step, but I'll go through all of them to show you how you can identify triangles. And I believe once you know how to identify them, then you can be able to prove that those triangles are similar using methods that I've taught you on how to prove similarity using angles. So the most important thing now is for us to know how to identify them. Now, we rewrite this as PT squared is equals to PA times PB. We break the PT squared into PT times PT is PA times PB. Now, you divide by PT. Obviously, you don't need both of them. You need only one. So you divide both sides by PT. If you check on the right-hand side, we already have a ratio PA over PT. And on the left-hand side, we only have PT because these two would divide out. So in order for us to have a ratio on the left, we need to divide by another side. We can use PB. We divide by PB here, then we'll get that PT over PB is equals to PA over PT. This is the proportionality that is implied from the statement. Now, in order for you grade 12s to identify the triangles here, you need to use the following two methods. One of them would always hold for a specific proportional side. Now, we can take, if we take the top sides, if you check here, I have PTPA letters on the top. I can take these letters to form a triangle. If you check, I have letter P, T, P, and A. So P, because it appears twice, I'll only use one. So this gives me triangle PTA. I check on the diagram whether PTA is a triangle. PTA. It is a triangle. Then from there, I go to the denominators on both the left and the right, I see this is PBPT. Because P appears twice, this would be triangle PBT. I check whether PBT is a triangle. PBT is indeed a triangle. So I will prove that these two triangles are similar, and hence I'll be able to conclude that statement. You can either go from left to right on the numerators, left to right on the denominators for the next triangle, or you can go for the whole ratio on the left. Let's check our whole ratio on the left. It gives us P appears twice, so this would be PTB. P, you check PTB. It is a triangle. And then we go on the right, we check P appears twice, so this would be PAT. So we've identified the two triangles that we can prove to be similar for us to be able to conclude that statement. So after identifying them, you prove that they are similar, and then from there, you use your smiling face approach or method to show that the sides are in proportion. Right. Let's move on to the next one quickly. I just want to lead you into identifying triangles, or assist you to identify triangles. This problem is similar to the one that we just did. It is similar to the one that we just did. So I'll leave this one and move on to this last one, which is a challenge question. We want to do the same thing here. We want to identify triangles. We are given on one the ratio of sides, and then on two, or rather on one we are given the sides in proportion, on two we are given the products that are equated together. Now we start with AD over BC. We are happy with this one because they've already written this as proportional sides. Remember in the previous problem, in this problem, they did not write it as proportional sides. We were supposed to move from this statement to that. But in this one, they simplified everything for us. Now we're going to try and identify triangles. Now, when you look at the numerators on the left and the right hand side here, you see that this is ADBP. There's no letter that is repeated, and this is not a triangle. If you also go for the denominator, you can see that this is BCP. Obviously, with this one, we have a triangle. But this triangle should be proved to be similar to another, and we don't have the other triangle. So this method in this case will not work. If you then look at the numerators, or rather look at the proportional sides on the left, you see that this is still ADBC, which is not a triangle. This side as well would get BCP, which is a triangle. But this triangle should be proved to be similar to another triangle. In that case, we see that both our methods that we know that we want to use to prove similarity are not going to work. However, if you check on the given statement, there are equal sides. DP is equals to PB. And in that case, it would mean, grade 12s, you are going to go to your statement that is given, BP over CP. CP. You replace BP with DP. We replace BP with DP. After doing that, you can see if you go for the numerators, you get ADP, which is a triangle. If you go for the denominators, you get BCP, which is also a triangle. And you can use those two triangles to prove similarity. We have run out of time, grade 12s. However, you've seen that it's important for you to know how to identify triangles. It's important for you to know how to prove similarity using corresponding sides, as well as to prove similarity using angles. Thank you for watching this lesson. Remember to sanitize, wear your masks, maintain social distance, and keep safe. Love mathematics.